So thank you very much for joining us today, and welcome to this webinar, How G3 PLC Addresses Global Regulatory Requirements. My name is Leon Vergeer, and I'm the General Secretary of the G3 PLC Alliance. Before we start, we will share the recording of the session with all the participants, and also the presentation we will use. And before going to the real experts, let me briefly say a few words about the G3 Alliance and the G3-Hybrid solution. So this illustration shows the evolution of G3 PLC. The alliance was formed in 2011, and around that time also the G3 protocol was adopted by ITU and published as G9903. A few years later, additional PLC bands were introduced. First, we targeted India with a frequency 863 megahertz, and in 2020 we introduced the G3 hybrid solution. Sorry, we introduced a hybrid solution, first targeting India with the 863 megahertz, and we are really pleased this year. The specification and certification has been extended by adding additional RF frequency bands. And this makes the G3 hybrid solution a real global solution, complying to regulatory requirements in any part of the world in a wide range of applications. And that will be explained in the webinar today. So for the people who are new to the hybrid solution, what is hybrid communication? The hybrid solution combines PLC and RF communication in one single solution. In the illustration on the screen, you can see a hybrid PLC and RF mesh network, and each device can use PLC as well as RF for the communication. And for each individual link, the best available medium is selected automatically and adjusted dynamically depending on the actual conditions in the field. It's important to understand that the G3 hybrid is a single solution, so it's one platform and not dual mode communication with two modems in one product. Here you see the protocol stack for G3, and this shows that it's really a single unified hybrid PLC and RF stack. At the bottom you see the physical layer, next to on the left the PLC physical layer, and on the right the RF physical layer. And a little bit up you see the hybrid abstraction layer in the stack. And the hybrid solution automatically at that level makes the decision to use PLC or RF for the communication. It's a fully standards-based solution. The protocol was published by ITU. There is a certification program in place by the G3 PLC Alliance, and we have already quite a number of certified hybrid solutions, platforms as well as products. So I'm very happy to introduce to you Klaus Huesk and Rafael Kerbrat, who prepared today's webinar. Klaus is engineer at Renesas, and Rafael is engineer at STMicroelectronics. Together they lead the regulatory and advisory working group in our alliance. And in this working group, several members of the alliance work together to investigate the regulatory aspects related to PLC as well as RF. So that for the introduction, I will quickly hand to Klaus and Rafael. They will start with presenting all the RF frequency bands supported by the latest release, and then under item 3 in the agenda, present the regulatory requirements in the different regions around the world, and they will explain the mechanisms which have been introduced to address these regulatory requirements. And then after that, there should be some time for questions. If you have any questions, please post them right away in the question box on the webinar system, and then we will try to answer them maybe during the presentations, or if we don't have enough time, we will answer them afterwards. So then, Raphael, I think I like to hand to you to start.
Yes. Thank you, Leon. Perfect. So let's start with the regional regulations. So the ITU, which is the International Telecommunication Union, it's an agency of the United Nations, define 3 regions in the world for the regulations. So there is the region 1 with the Europe and Africa, region 2 with North and South Americas and the Greenland, and region 3, which is represented by India and most of Oceania. We will use this split later on in this presentation to show you some examples of regional regulations. Then we can move to the next slide. Okay, now is the frequency band definition, sorry. So the G3 PLC hybrid specification uses for the RF the sub-gigahertz technology. So the band is all the RF concerns the RF frequencies below 1 gigahertz. More especially, it uses a physical layer based on the 802.15.4 specification from the IEEE. The 802.15.4 defines the Sun FSK phi, which is used by the G3 PLC RF. This physical layer defined by the IEEE 802.15.4 defines some frequency bands, as you can observe on the table on the right. So this table is directly extracted from the standard, and you can observe here the bands which are already, let's say, where the requirement is already met by the G3 PLC hybrid standard, and those which are still under investigations in the workshop 4. So how does it work? In the specification, there are some band designators. You can observe, for instance, the band designator 863, which is for the European regions. Design the frequency band 863 to 870 megahertz. What is important to know about this table is that, okay, there is the mention of the region, but this is informative only. It's not let's say, definitive information. If you want to add a country which is not listed in this table, for instance, you need to know the frequency band which rules in this country, and then you need to make it as a subset of an existing designated band in the IEEE 802.15.4. So this is quite simple. If there are forbidden frequencies in the new region you target, like in the middle of the band or in the low or high frequencies, then you can use channel masking to make them not available. So let's move to the next slide then. Because now we know in which band we can operate, and the band which are already defined by the G3 PLC hybrid specification. Now we will discuss about the RF configuration. So as well, the IEEE 802.15.4 defines in the Sun FSK physical layer some modes, some operating modes. For each mode, they are define the data rate and the modulation index. So based on those information, we know the frequency deviation used for the FSK modulation. You can take as an example the first table on the right, which is the mode definition for the frequency band 863. You can see that mode 1 has data rate of 50 kilobit per second. The modulation is 2 FSK. Anyway, for the hybrid solution, all is 2 FSK. Then the modulation index is 0.5, channel spacing is 100, and frequency deviation, in this case, based on those settings, is 12.5 kilohertz. What has been defined in the ITU 9903, so the other name of the G3 PLC, the official name of the G3 PLC hybrid standard and specification, is that the mode 1 for any band is the mandatory mode. So for any region, the mode 1 as defined in the IEEE standard is necessary to be applied. Then there is an optional mode, also called the high data rate mode, which is selected among the available operating modes as defined in the 802.15.4. For instance, there is also on the right a second array. So with the definition of the 3 first mode of the 915 band, you can see that for the 915 band, we have selected the operating mode 3 for the high data rate. That means we can operate at 200 kilobit per second. For the 863 band, we have selected the operating mode 2, so we can go up to 100 kilobit per second as data rate. This is purely for RF, let's say, constraints, because mode 3 is very hard to achieve because of the channel spacing, which is very low in this case. So now we can move to the next slide. And to the next section, so the third section. So now we will focus on the regulatory constraints in different regions around the world. Introducing to the Alliance members the documents which are available for their reference for the implementation of any RF regulation. Then we will go further in details on some specific regions in Europe, Asia, or Americas. And we will describe the dedicated mechanisms implemented in the G3 PLC hybrid specification. So we can move to the next slide and start with the regional regulations clause in the IEEE 802.15.4 standard. So there is one clause that mentions that it's not it's the responsibility of the implementer to make sure the device is in compliance with all regulatory requirements in the area where the device will be sold and deployed. So that's the responsibility of the implementer to pass the regional regulations to be able to affix the proper marking on his device. As you can see in the middle of the slide, the CE marking, for instance, in Europe, the FCC marking in the US, and the Japanese marking for the Japan, especially. Then he will have to pass the, let's say, the related regional regulations. And we can mention, for instance, some well-known and the main regional regulations, as in Europe, the ETSI EN 300-220 or EN 303-204. In the US or Middle South Americas, the implementer will have to pass the FCC certifications, parts 15.2.9 and 2.7. In Japan, it's the governmental radio law which applies, and in China, it's the SRRC. But definitely, there are many other specific regulations in other regions. And in this case, the implementer have to contact directly the regional regulatory administration to know the details of the requirements that applies in the region. Then the implementer needs to come back to the workshop 4 or the G3 Alliance to have, let's say, the confidence that the regulation is, let's say, applicable in the current G3 PLC specification, or if any change or update has to be applied. Now, the good point is that the G3-Hybrid specification has anticipated the support of regional regulations because there are some parameters that the manufacturer can configure. That's the way to adapt to any targeted region on our market. So now let's move to the next slide about maybe the first parameter to check for the regional regulation, which is the band usage. Let's have the example of the US band plan. So as you can see at the bottom of the slide, there is the band plan in the US from 300 megahertz to 1 gigahertz. As you can observe, it's crowded and well occupied, and the ISM band, which is the license-free band name, ISM meaning industrial, scientific, and medical band. So this license-free band is very small compared to the others, and as you can imagine, as it's license-free, it's very crowded as well. There are many devices using this band, let's say simultaneously. So this is a real challenge to correctly perform in the license-free band. So how to get some more insight of the ISM band? So in the US, it goes from 902 megahertz to 928 megahertz. So there is a 26 megahertz bandwidth. Sorry. The channel spacing we saw in the previous slides, that as defined in the 802.15.4, the mode 1 defines a channel spacing of 200 kilohertz. That means there are 129 channels available in the band. In mode 3, as the data rate is higher, the channel spacing is as well higher, and up to, it is actually 400 kilohertz. So there are 64 channels available. So the implementer must use, have a, let's say, take benefits of those channels to be able to coexist with the other device already using the same band. And the regulation will define as well constraint on the ISM band usage to limit the channel occupancy. Those, let's say, constraint will be the duty cycle, so the time you will transmit over a given period. There is the listen before talk as well. It's a way to prevent the transmission if another is already transmitting. And there is the frequency hopping, which is a way to spread the transmission over channels inside the band, and to spread as much as possible the usage of the band. So those are the, let's say, the topics or the characteristics of the regulation related to the band usage. Then we can move to the next slide, where we can see the characteristics which are related to the reception of the device. So there are mainly two key parameters for the reception. So the receiver requirements concern the receiver sensitivity and receiver interference rejections. So those settings are mainly defined for region 1 and 3. In region 2, there are no RX conformance tests for the regional regulations. So let's now define what is the receiver sensitivity. So it's straightforward. It's the, let's say, the weakest signal that the device can receive correctly. So at a given, let's say, error rate limit, you can see on the right of this slide the test setup, which is used by the certification laboratories to pass the regional regulation. So for the sensitivity, we can stick with the green part of the setup. So there is one signal generator sending a modulated signal to the device under test. And the device under test will send the demodulated data to one computer, The computer, knowing exactly what is the modulated signal sent by the RF signal generator, will be able to compute the bit error rate at reception. And once the signal generator has, let's say, we decrease the level of the output of the signal generator step by step, and once the bit error rate limit is achieved, we have measured the sensitivity limit. So that's the way it is done. Then there is the receiver interference rejection, let's say, characteristic. It's to ensure that your device will be able to receive whatever the, let's say, the interferences inside the band or even outside the band. So there are some, let's say, given offsets which are taken by and defined by the regional regulations, where you consider that you have one interferer that transmits at one given level, and you want to ensure that you won't impact the sensitivity of your device. So I also put the setup on the right of this slide. You can see that, okay, the principle is the same as for the sensitivity measurement, but you add one generator with an unmodulated, let's say, a continuous wave acting as an interferer. So it's the way to perform the test, basically. So we can move to the next slide with the TX characteristics. It's another topic of the regional regulation, but it's a very important one because for sure the regional regulation will not allow you to do anything with your device when you transmit. Otherwise, you can pollute all the RF, the related band. So there are some limitations about the transmit output power, as well for the transmit spectral mask to not interfere with the adjacent channels or even outside the bands with the harmonics of the output signal. And then, yes, the spurious emission as well. Then the test setup is straightforward because you use the device under test, and it's only plugged to a spectrum analyzer, and it transmits at the maximum output power, which is stated by the manufacturer to the certification laboratory, and then the spectrum is checked carefully to be inside the spectral mask as defined by the regulation. So we can move to the next slide, because here is the work we've done with Workshop 4 to try to synthesize all the regional regulations into one table. So we have gathered what we have found as the topics that are mentioned in every regional regulations. Some are often not specified, but we have we try to list all those parameters. And then for each region, we complete the checklist. That's a very convenient way to compare the regional regulations one between others. And it's also a way to quickly find out what could have an impact on the G3 specification itself. So it's a very useful tool because we don't have the information anywhere else on the internet or or somewhere else. So that's what we use internally for our study. In order to share this material with the rest of the G3 members, we can go to the next slide then to show you and to announce that we have written a white paper called the RF Regional Regulations Study that gathers the work we do in Workshop 4 to make it available to all the members of the G3 PLC Alliance. So from today, it's available on the website. You can go to the link here, and you will be able to read this this document. As you can see, in the table of contents. So we have gathered all the regions that we have studied so far, and you will have a quick access to your region of interest. And for sure, if you need support or if you have any question regarding this document, you can contact us at our workshop for address. You will see it at the beginning of the document anyway, as reference. So in the next slide, we will give you an overview of some regional regulations that you could, you would like to use for your devices. So let's start with Europe with the next slide. So in Europe, what is basically the regional regulation? So the constraint about let's say the most common regulation in Europe is the EN 300-220. It defines an output power of 40 dBm. So it's the maximum output power you can achieve with this regulation, but only in a very, very small range from 869.4 megahertz to 869.65 megahertz, so only 250 kilohertz. You can output 27 dBm, but it's a very small range, which is not, let's say, there is no point to use that for G3. Then we can discuss the constraint about the transmission duration with EN 300-220. So the maximum transmission time for a single transmission is 1 second. For a dialogue, so with another device, is 4 seconds. And there is an off time minimum of 100 milliseconds. Then there is also constraint on the maximum duty cycle. So the maximum transmission duration during a given listening period is 100 seconds per hour per 200 kilohertz bandwidth. So that's the status for the EN 300-220. Then let's talk about the EN 303-204, which is very convenient because it allows to transmit up to 27 dBm, only in the range 870 to 876 megahertz. The drawback is that, so far it's not available in all European countries, as you can see in the table in the bottom of this slide, coming from the European Research Council. So it's the recommendation 7003. You can see that for the moment, the implementation is not agreed for every country. But anyway, if you want to use it, it's worth you contact directly the regional, the country of interest and the regulatory administration. For this EN 303-204, we can check that the transmission duration is maximum 400 milliseconds, as well as the off time, which is must be higher than 400 milliseconds. For the duty cycle, the constraint is the same. It's 2.5% for any kind of devices, but 10% for the network access point, because they have more, let's say, throughput with the outside of the network. What is important to notice as well for the EN 303-204 is the APC limit. So it's the adaptive power control. So it's a way to avoid transmitting at maximum output power of 27 dBm all the time. But I will let Klaus give you more inputs about this feature later. And I will give the floor to Klaus to give you also details about the duty cycle management in G3.
Thanks, Raphael. So I think that's already quite a lot of information to digest, but unfortunately we are not there yet, so there's more to digest. So maybe let's move to the next slide then. Here we go. Okay, so as Raphael already pointed out, so the ISM band has regulations regarding channel access and other mechanisms. So one of the key aspects in the ISM band is fairness. So that means the ISM band is shared amongst many different services and different nodes. So then the regulation has to make sure that all services can operate in that ISM band simultaneously without interrupting or interfering with each other. So then one of the key features is so-called duty cycle. So apparently if few devices would transmit all the time, so others cannot transmit, so they would be interrupted in their services. So that's why commonly the regulation limits the transmission time per node, and this time is defined in a sliding window, which is then referred to as a duty cycle. So in the previous slide, we have seen that, for example, for EN 303.204, you have typically duty cycles of 2.5% up to 10%, but in different geographies in the world, so the duty cycle can be lower or higher. But typically there is a limitation of some sort. So that means we can only transmit a given time in a given sliding window. So the sliding window is commonly 1 hour. So then the limitation is several seconds that we are allowed to transmit in that hour. So transmitters need to keep track of the time they already transmitted and make sure they do not exceed those limits. And one of the main things that the workshop 4 is looking at is, does the G3-Hybrid specification already provide all the required mechanisms to address those regulatory requirements? And indeed, in the G3-Hybrid specification, there is a dedicated mechanism to deal with duty cycles. And these are basically two approaches. So one approach is to share the duty cycle information with neighboring nodes. So that means node 1 will keep track of its already consumed duty cycle and will propagate that information to its neighborhood via a so-called information element. So this is the link information element. So that is containing the duty cycle consumption in percent. And node 2 can then take any action on this information. So there's also a local mechanism what a node can do if it's close to reaching its allowed duty cycle limit. So since we have a hybrid system, so what we can do is we can always fall back to PLC if available. So that means if we reach a specific threshold of duty cycle usage, we disable the RF transmissions and fall back to PLC. So this threshold is by default 90%, and it's 90% because there's supposed to be some headroom for acknowledgement frames that will be sent for relay nodes. But that's a configurable threshold anyway. So let's move to the next slide. Thank you. So the information that the nodes share between their neighborhood, that can be used to actually influence the route creation in the mesh network. So as you know, the G3 technology is based on layer 2 routing protocol called LoadNG. And the LoadNG route metric can be influenced by different parameters, which then take into account link quality or modulation type, and so on. And for the hybrid, there was some new parameter added, which is the ADP KDC, where the DC apparently stands for duty cycle. And this means the duty cycle information is then also used for route creation. So the intention here is to prefer nodes that have low duty cycle consumption and make nodes unfavorable that already have a large amount of its duty cycle limit reached. So there is a simple example here. So we have two potential relay nodes, 1 and 2, and node 3 is now creating a new route. So then as part of its link cost computation, it will compute the link cost penalty for the duty cycle. And apparently if the duty cycle usage is 0%, so then there is no penalty. So it's the optimum, so penalty is 0. But for example, at node 2, the duty cycle budget is already 50% depleted. So then it would lead to a link cost penalty of 5. with a default value of 10 for ADP KDC. And just to provide a hint on what that means, link cost penalty of 5. So you always have a penalty of 4 for each hop that you create in the network. So then if you already have a penalty of 5, so that means that node would prefer an additional hop rather than going to node 2 because of the high duty cycle that it already used. So this is to make sure that the duty cycle consumption is leveled throughout all relays in the network. Okay, I think we can go to the next slide. So the other mechanism that Rafael was mentioning was the adaptive power control, abbreviated as APC. So the transmit power is one of the key parameters in RF regulation, and in many regulations it's very limited, for example to 20 milliwatts in Japan, or 25 milliwatts for EN300 220. But then there is other regulation, for example the EN303-204, which allows 27 dBm, or commonly regulation in the Americas following FCC rules allows up to 30 dBm. But apparently that's good to have, but it's not always needed. For example, if devices or nodes are very close to each other. And if that's the case, so then the high transmit power can even be have negative impact on the communication performance of the whole network. So there's a simple example on the left-hand side where we don't have any adaptive power control. So let's assume 4 nodes which are part of a network. So node 1 is communicating to node 2 by a good link with a transmit power of 30 dBm. And node 4 is communicating to node 3 over a poor link with high attenuation, also with 30 dBm. But then the problem is if node 1 is close to node 3, so then the signal transmitted by node 1 will interfere with the received signal in node 3, which is originally set by node 4, which makes then the communication impossible or very bad performance. So to avoid that, the idea is if we already have good links, for example, between node 1 and 2, so we reduce the transmit power gradually to the level that is just required to have good performance on that link, while minimizing the interference with other nodes in the network. So that's exactly displayed on the right-hand side with APC. So then node 1 is reducing its transmit power to 7 dBm, which then has still good communication with node 2, and also doesn't interfere with the communication between node 4 and node 3. So how's that done in G3? So that's described in the next slide. So we have information that is exchanged between the nodes, which is called the LQI. So the LQI is basically a mapping of the receive RSSI on the receiver side. So for example, if node 1 transmits something to node 2 will measure its RSSI and provide that information back as part of the RQIE, which then lets node 1 and the transmitter know how is the receive level on the receiver side. So then there is a mechanism specified in G3-Hybrid, which defines some thresholds like the MAC adaptive power high bound and adaptive power low bound, which are then used to gradually adjust the transmit power. So in this example here, we assume that the MAC adaptive power high bound is 104. So then the transmitter would try to reduce its transmit power up to the point where the reported LQI that comes back over the RQIE is exactly 104. And this is done in several steps. So from one step to the next one, the transmitter will reduce the power by 3 dB until it achieves a stable level. So that way we can make sure the transmit power is only that high as it's needed for stable communication. So if the channel conditions change and the communication becomes unstable, there is a fallback mechanism which gradually increases the transmit power in case of missing enhanced ACK frames. So then we can adjust to these problems in communication between 2 nodes. So just a small remark, so the APC mechanism is completely configurable and can also be deactivated by setting the corresponding attributes to 255 and 0. So I think then back to Raphael for the next region.
Yeah, thank you, Klaus. Next region is Americas. So quickly for this region, it's what we can say is that most South American countries are under the regulation of ITU Region 2, so they are acting as well in the 900 megahertz band. So what we assume in the workshop 4 is that the FCC regulation applies for both North America and South America. So the main rationale behind is that the lack of information we have for some South American countries, but also we know by experience that many South American countries already use the FCC regulation. So this is the reason for this assumption. And what is very interesting in the US is that, okay, we can, as said by Klaus, we can transmit up to 30 dBm, but there is a high duty cycle constraint. To overcome that, we can use the frequency hopping feature to implement data acquisition network. Also, with the use of frequency hopping, yes, we can. This is the way to use the transmit output power up to 30 dBm, and that's an asset for longer range connectivity. I will leave the floor now to Klaus again to show the frequency hopping management.
Okay, thank you. Yeah, so quick introduction to what frequency hopping is. So considering the time, we shouldn't spend too much here. So apparently what we have is a frequency band, let's say the 863 to 870 megahertz band or the 902 to 928 megahertz band in the US. So this is split down into dedicated channels. So Raphael already mentioned in the US band, you have 129 channels. So one straightforward way of using the system would be to use fixed channel operation. So then you pick just a channel and operate the whole system on that single channel, which is predefined. So that's quite simple, but it comes with some drawbacks. So if you only operate on one channel, the selected channel will be heavily used, so you have a high chance of collisions. So then eventually, since we have many other systems operating the ISM band, that channel may already be used by other systems or affected by interference. So that means you cannot really escape poor channel conditions if the channel is pre-configured. And it makes it very difficult to use the full band efficiently, because then you would need to manually split the band into channels and assign it to different subnetworks. So then one solution to this is using frequency hopping. So next slide, please. So what is frequency hopping? So as we know in this example, we have 8 channels. So then hopping means we hop through all channels of the frequency band over time. And the hopping sequence is pseudo-random and makes use of the entire frequency band. So we hop from one channel to the next one over time. So the benefits of this is that each channel will only be partly used. So it will only be used over a short period of time. So fewer risk of collisions. So then poor channel conditions will be mitigated because we only use that poor channel for some subset of transmissions, and the full band is evenly used with this technology. So that's all nice features, but then how do we make sure that transmitter and receiver know which channel to use at what time? So that's the key challenge of frequency hopping, which we will have a look at the next slide. So that means to make sure that transmitter and receiver operate on the same channel at the same time. So the time synchronization between the nodes is key. So the time is divided into slots of equal size, and the channel is changed in each time slot. So the time information, which is given as a slot number and the offset of time within a slot, is exchanged via the new FHT information element. So it's a frequency hopping timing information element. And that timing information is exchanged between the nodes. In this example, node 1 and node 2, which then makes sure that the transmitter knows at which time the receiver switches to the next channel. So the actual transmission channel can be computed by a so-called channel function as a pseudo-random sequence. And that function takes as the input the slot number. So that's why the time information is key here. The short address of the device and the PAN ID of the network that is currently operating. And that input is known to both node 1 and node 2 because of the time synchronization. So the outcome will be the same channel. So that means this example, when node 2 transmits something to node 1, the transmit channel is computed as a function of the address, the PAN ID and the slot, and results in usage of channel 8. And node 1 will follow the same sequence. So that's why node 2 can communicate to node 1 without problems. And that's basically a brief introduction of how the frequency hopping is realized in the G3 hybrid specification. Okay, back to Raphael.
Yeah, thank you. So the last region now is the Asian region. We will start with the case of Japan. So in Japan, the short range devices can operate in the 920 MHz band. Regarding the law, the governmental law, we have selected the part 2 as the most appropriated to the regulation, is the one for low power radio stations. And what is interesting is the duty cycle that can be increased by having at least 2 transmission channels, and that for sure can be used activating the G3 hybrid frequency hopping mechanism. Then on the next slide, we will take the example of 3 other Asian countries, the Malaysia, Indonesia, and India. So just to give you a quick brief overview. In Malaysia, for instance, the 916 to 924 MHz band is split into 3, with, like already seen for other regions, some constraint on the duty cycle that can be overcome using frequency hopping or listen before talk feature. In Indonesia, the 920 to 923 MHz band is used for the SRDs. And what we can see is that the radio standard is a mix of FCC or ETSI, so non-standards that we know are already supported by the G3 PLC hybrid specification, of course. Then in India, for the last part, the frequency band is 865 to 868 MHz, and the radio standard is based on ETSI. What is interesting is for the Indonesian case that the IEEE doesn't define this region. So as said in the very beginning, as this region was not stated into the band definition of the IEEE 802.15.4, we have decided to use the 920-B band to support the Indonesian case with the proper modes definition. So that's all for the regional regulations overview. I will give the floor now to Leon for the certification.
All right, thank you very much, Klaus and Raphael, for presenting all the regulatory requirements and also for explaining all the mechanisms we introduced in the specification. The new certification version of the G3 hybrid solution will be released in the first quarter of 2023, so the first quarter of next year. And this new version will include, first of all, the additional frequency bands as are shown in the table on this slide and were explained earlier by Raphael in the tables. Secondly, the certification version will also include the mechanisms presented in this webinar: frequency hopping, adaptive power control, and duty cycle handling. And furthermore, the new release will include the last gasp mechanism based on the RF technology. It will introduce a new profile for the hybrid targeting the Japanese market, because it uses the ARIPE band plan for the PLC. Performance testing was already in the certification for PLC, but will be included as well as for RF in the next release. And next to that, there will be improvement in general of the test coverage for conformance for both PLC and the RF part. So that will all be in the upcoming new certification release, which we are working on currently with the test labs and with Trialog to develop the test tools. And they will be available for certification in the first quarter of next year. And we will inform everybody about this in the coming period. So that's about a new release for the certification. Then, as a kind of a summary or conclusion, the G3-Hybrid is a fully fledged RF as well as PLC mesh communication solution. It combines PLC and RF in one single solution, maximizing the coverage and connectivity of the network, while at the same time reducing the cost and complexity of the installations. It's standards based. We have certified implementations already available, providing interoperable products for the installations. And as we explained to you in this webinar, the G3-Hybrid is a really global solution, complying to the regulatory requirements in any part of the world. So it's a very useful technology for smart metering and many other applications you might be looking into. So please, if you let's take a look if we have any questions. Some questions were very specific, which I answered already directly to the people, but we also got a few other questions already, and we have a few minutes to look into those. Klaus, maybe the first question I can pose to you. Maybe we answered it already partly in the presentation, I think. The G3-Hybrid option to work in ISM band region 2, 900 to 928 megahertz. What can you say about that?
Yeah, so the 902 to 928 megahertz band is now fully supported by the G3-Hybrid specification. And for operating in that band, which is the main band used in US and other parts of the Americas, is the frequency hopping mechanism, which has been introduced recently in the specification, and will, as you mentioned, be part of the upcoming certification program, which is available next year. So that's fully covered by the technology and certification by then.
Yeah, perfect. Another question we had, Rafael, maybe you can help with that one. What is the available RF bandwidth? Is it compliant with FCC 15.xxx or EN 300-220? And it's also mentioned IEC 16950/1.
Okay, so let me take it. Yes, so the RF bandwidth is defined as shown in the presentation first. So it's based on the IEEE 802.15.4, and for sure it's in compliance with FCC part 15 and EN 300-220. There is no problem with that. Regarding the last specification mentioned in this question, so from what I know, what I've checked, so need to be verified maybe, but the IEC 60915-1 is no more supported. There is another one, but anyway, it's a safety related regulation, so no worries that it's possible to get it certified along with the other RF RF certifications.
Yeah, I think the question was relating specifically to Thailand, I believe. So also there are no remaining open issues, if I understand correctly. It's fully compliant with the regulation there as well.
Yes.
Yeah. All right. All right. We have a few minutes left. If you have an urgent question, please you can still post them. We can have a look, or we will answer them after the webinar. Another question is a little bit more generic. It's not specifically related to the regulation or the new mechanisms, but related to the use of the hybrid solution. And the question is how to use more or less hybrid nodes to achieve good performance in case the PLC performance is not so good due to the environment. So like we already mentioned earlier, I believe that the hybrid solution is fully backwards compatible with existing G3 PLC specification and implementations. So it is possible to add hybrid nodes in a G3 PLC existing network, and by doing that you can indeed improve the performance of the network by using in specific instances the RF medium. Though in general, I believe that in our discussions with our members, normally when they talk about implementing the hybrid solution, it's mentioned that they plan to implement a full hybrid implementation, so with 100% hybrid nodes, and not mixing hybrid and non-hybrid nodes in the field, but installing 100% hybrid nodes, which can all use RF as well as the PLC. So that's the common installation approach, I believe. Another question to close with, I think, is there any real deployment with G3 PLC and RF hybrid which had node count above 5,000? Well, as we explained already, the hybrid solution is of course a relatively new solution. It was only specified in 2020. We have the certification in place now, and we have the certified products already available. So many projects are starting using the hybrid solution. Many pilots are starting in different areas of the world, but there have already been quite a few larger implementations, and you can find some specific information about these on our website. For example, ADD Group was very early with the first hybrid implementation in if I remember correctly, Middle East and Russia, where they implemented thousands, tens of thousands of hybrid devices, and they showed very good results in very tough environments, tough both for PLC and RF normally. And also some other members did some quite big implementations with I believe thousands of nodes in Russia, for example, earlier. And you can find further information about that on our website if you go to the page with the hybrid solution. So I think that's it for now. Thank you very much, Klaus and Raphael, for preparing this webinar, and for also for publishing the white paper about the RF regulation. And also a big thanks to all the other members who contributed to this white paper by providing specific information for particular regions or countries. So for the members, please download the white paper from our website. Soon we will also share the recording of this session and the presentation and the link to the white paper and to all the people attending. So thank you very much for attending. If you have any further questions, please don't hesitate to contact Klaus, Raphael, or me for more general questions. And we hope to meet you soon in Europe, or meet you again soon in one of the upcoming future webinars. So thank you very much, and hope to talk to you soon. Bye-bye.
Thank you, Leon.
Bye-bye.
Bye.
Thank you, Leon. Bye-bye.
Thanks. Bye-bye.